So Mathematica gets used for all kinds of things in the world today, pretty much wherever top-of-the-line R&D is happening across pretty much every industry, all over technical education and so on. But it's interesting. I mean, even though Mathematica first appeared 23 years ago, I still think that in some ways, for better or worse, it's a bit of an artifact from the future. I mean, in designing Mathematica, I've always thought it was a little bit like doing natural science. You sort of start from all the computations that one might want to do, and then sort of drill down underneath those computations to figure out what primitives one can use to set things up, to build up all those kinds of computations in convenient ways. Underneath Mathematica is a very general idea, the idea of symbolic programming, the idea that everything one manipulates in the system, whether it be data or documents or graphs or programs or whatever, can always be represented in a single uniform way as a symbolic expression, and then manipulated using a sort of coherent set of primitive operations. It's actually taken me sort of decades to understand just how general and powerful the idea of symbolic programming is. And it's brought us all sorts of innovations, and it's a core part of what's made Wolfram Alpha possible. You know, from the very beginning of designing Mathematica, I had some sort of fundamental principles which I'm happy to say have been able to continue to guide our development ever since. One of those principles was our job is to automate as much as possible. So we want the human to define what they want to do, but then we want Mathematica to take over from there and sort of automatically figure out as much as possible about how to get the things done. So whether it's which of 100 possible algorithms to use in some particular case for some particular problem, or how best to lay out a graph, or how to set up an interface, or whatever. Because it's by automating as much as possible that we as humans get the most leverage out of our system. Another principle, which I have to say I have personally put years of my life into, is sort of the principle of maintaining unity in the design of the system, making sure that all the sort of many capabilities of Mathematica all consistently fit together. I have to say that particularly in recent years, it's amazing how well that's paid off. Not only for people learning and using the Mathematica language, but also for us in building the system ourselves. I mean, our sort of general idea for Mathematica has been to sort of build into it essentially any general algorithmic procedure, whether it's for graphics or statistics or image processing or control theory or sequence alignment or whatever. And by now, we certainly have by far the world's largest and broadest web of algorithms, many of which we've actually invented ourselves. But the point is that everything sort of fits together. So when you want to add something in one particular area, we immediately get to leverage anything in any other area. It's been exciting for us internally to see that sort of exponential development that gets made possible, and that, among other things, has made Wolfram Alpha possible to build. Well, Mathematica has been used for lots of sort of industrial scale applications over the years, and so it's got a very robust development and deployment mechanism, which meant that for the sort of when we built Wolfram Alpha and set up its kind of supercomputer type infrastructure, we basically just had to turn on our standard Mathematica deployment mechanisms to have that all work. It's interesting from sort of a user point of view to compare Mathematica and Wolfram Alpha. I mean, Mathematica is this very precise language where you can sort of build arbitrarily deep, complex structures and so on. Wolfram Alpha is a very broad system. I view it as sort of a drive-by system where people are just entering some quick thing and getting a quick answer, but it handles all of that messiness of the world. So it's really interesting to see how to sort of bring these two very different design modalities together. So for example, now within Mathematica, you can call on Wolfram Alpha capabilities. So that means, among other things, that you can type sort of free-form natural language and have it automatically translated into precise Mathematica code. I think that's a pretty exciting development, including for areas like biology, because it really breaks down the barrier between programmers and non-programmers. It lets anyone sort of build up programs step by step, just using sort of free-form natural language input. So, well, right now we're sort of in a remarkable situation. We've got sort of oodles of technology that we've been assembling for the last 25 years, and it all seems to be coming together very much at once and letting us do all sorts of fascinating things. And another thing we're doing is a thing we call CDF, our computable document format, where we get to use symbolic programming to make sort of an incredibly easy way to create computable interactive documents. And I'm probably going to get upset again because the network is probably going to do badly again, but we'll give it a try. Oh, something happened. Okay. Well, the idea here. Let's go. Let's just go back here. So what I showed was a site with about 7,000 examples of this computable document format, and each one of them is something that can immediately be made interactive. And what's interesting is that we're seeing that sort of papers and reports and so on can be made interactive. It's a bit like what happened with typesetting of documents 20 years ago. It went from being a thing that one had to have a specialist do for one to being something that a typical person or researcher or whatever could do for themselves. That's what CDF is now making possible for interactivity and computability. You don't just have sort of a static curve in a document. You have something where you can drill down, adjust the model, and so on. So the real kicker to this is that you can actually start creating that interactivity using Wolfram Alpha technology just by entering free-form natural language. And by the way, you'll be able to have your data uploaded to the Wolfram Alpha cloud to be accessed in CDF and in Wolfram Alpha, as well as through the Mathematica language. So these things all begin to come together. Well, you know, I think it's sort of a pivotal year, actually, pretty much this year for the computer industry, with all sorts of new methods and platforms and so on coming online. I mean, cloud computing is one thing. Something that's becoming possible with what we're doing with Wolfram Alpha is what I call knowledge-based computing. Usually one thinks of constructing software sort of from raw computational primitives. But with Wolfram Alpha in the loop, one gets to start, in effect, from sort of all the knowledge of the world and then build software from there. Lots of interesting products in the pipeline that are doing that, notably, for example, in mobile computing, where the whole idea of being sort of immediately able to get exactly the knowledge one needs without sort of rooting around and searching for things and so on is particularly important. So it's always interesting. With every new kind of platform, there are all kinds of new ideas. I'll show you one example that comes from a spin-off company of ours called TouchPress, which I'm happy to say has been the, let's see if I can get this to work. Oh, no, that's just me. That's an iPad, but it's, let's see whether I can have this. Let's see how this works. No, it didn't work very well. I'm just going to show you the TouchPress has I'm happy to say, has published the so far #1 best-selling, highly interactive ebooks on the iPad to date. Here's one about the solar system, and you can go and click on it and roll around your image of the planet Mars, or zoom in on it, or go and take a look at where it fits into the solar system and roll it around, all those kinds of good things. Actually, in a couple of months, we're bringing out a rather unexpected bio-related kind of title that I think will be quite a lot of fun. Well, I might say, by the way, that the whole image processing and animation pipeline that's used for that interactive ebook was built in Mathematica, and we also end up using Wolfram Alpha for the background data for these kinds of things and so on. Okay, well, there's lots more I could say about technology. I want to turn now to basic science. After that, I'm going to try and bring all of these things together and talk a bit about what they might mean for the future of bio kinds of areas. Okay, so about science. I mean, I started out at a young age doing physics. Physics is in a sense a very, very arrogant science. It somehow expects to sort of find fundamental theories for everything. Well, what I realized at some point is that when the systems that I looked at were more complex in one way or another, not least in areas like biology, the methods that I knew from physics didn't seem to make an awful lot of progress. And so what I began to think, now about 30 years ago, is that if one was going to make progress, one was going to have to take a whole different approach. You know, in physics, there's really one big idea that's about 300 years old, which is that one can use things like mathematical equations to model the natural world. Well, if there's going to be any kind of theory for a system, the system had better be based on some kind of rules. But what I began to wonder was whether there are more general kinds of rules than the ones that we get from mathematics. Well, fortunately, in modern times, we have a framework for thinking about such things, programs. We can think about any kind of definite rule as corresponding to a program. But if one's interested in systems in nature, the question is, what kinds of programs correspond to what's happening in nature? When we use programs in practice, we're used to building up very complicated programs, millions of lines of code, whatever, to do very specific things. Question that I got interested in a long time ago is sort of a basic science one. If one somehow looks at the kind of computational universe of all possible programs, what do they typically do? Well, the best way to find that out is just to do an experiment. And for me, it was sort of a question of taking my sort of computational telescope, Mathematica, and sort of pointing it at the computational universe. So what does one see? Well, I started off looking at a very simple kind of program called the Cellular Automaton. And this is how it works. It consists of a bunch of idealized cells, each either black or white, arranged on a line. So the idea is that at each step, the color of each cell is determined by a simple rule from the colors of the cells on the step before. Okay, so what actually happens there? Oops. So this is an example of what happens, starting from a black cell at the top of the screen and then evolving down the page according to the rule that's given at the bottom there. So in this particular case, what's generated is a very simple pattern. Nothing very surprising. So we can try changing this rule a bit. Let's try changing that that case in the rule there. Then we get a checkerboard. Let's say we change this one here. Then we get some kind of more elaborate nested kind of pattern. But in a sense, we're still getting something that has some kind of regularity that we can think of as reflecting sort of the simplicity of the rule that made this pattern. But the question is, what else can happen in the sort of computational universe of possible programs? Well, it's pretty easy to do a computer experiment, let's say with Mathematica, to find out the answer to that. So here I'm just going to make a table of pictures of all the different possible cellular automata with rules of this kind. So there's the result. Each little picture here corresponds to a different rule. We can see there's lots of diversity in what happens. Mostly it's pretty simple, at least until one gets to this one here, for example. This is rule number 30, and it's probably my all-time favorite. Let's look at that one in a little bit more detail. Here it is. Starting just from one black cell at the top, we can make it run for a few more steps. Let me see what it's doing here.